So delighted to have all of you here tonight. I am very thrilled to bring you another fantastic Ventech event with our keynote speaker, Dr. Matthew Greenhouse, James Webb Space Telescope, NASA lead project scientist. It's going to be amazing, along with our fast pitch segment. I'm Jill Feldman. I'm board chair of Ventech and the president of Strategic Development Associates. I am thrilled to tell you that we have over 150 of you here this evening, which is amazing. And that's because we all believe in the same thing, that the Santa Barbara tech, business, and entrepreneurial community is strong, and we all want it to succeed. And now I am thrilled to begin our fast pitch segment, and we've been doing this for about almost the last year. It gives us a great opportunity to showcase a few of our local exciting startups. If you're interested in participating in the future, visit our website or use the QR code that was at the check-in desk and on the tables to access the application. And we have two speakers, Dan Casey from Dragon Q Energy, and he'll be followed by Nicholas Palufo of Traveler. And I'm going to bring up Dan first.
My name is Dan Casey. I'm CEO of Dragon Q Energy. We are developing a battery energy storage system, a grid battery, for extreme climates where it's hot. We hope that it's not hot everywhere for very long. We got to do our best to control that. Our awesome team, small team, is being incubated at California Nanoscience Institute. We're on the UCSB campus, and the CNSI group is absolutely wonderful. They're amazing, and they're very good to us. I'd like to start off with the solution. Dragon Q is prototyping an inherently safe battery energy storage system, or a grid battery. With that, we get efficiency as a grid operating platform. We have extra knobs to turn because of the pressurization of our containers, and that allows us to control the cells in different ways, ultimately leading to a safer grid battery. We're also differentiated by the ability to deploy the battery underground, as you can see. We're not proposing that our batteries are going to actually touch dirt. They'll be engineered earthwork, but we can use the stable environment below the surface to conduct heat away from the battery system. The problem. I think everybody sees it right there. Current grid batteries, what we call the ubiquitous white box, are complex, expensive, and they come with very long lead times. As far as expense, each of those white boxes are about $1 million. They have known failure modes, which I think we can see there. Fire. We referenced quite often a fire in 2022 in Moss Landing, just right up the coast, where a Tesla battery energy storage system caught fire from water ingress. Rain got in. So rain got into the battery energy storage system, started a fire. So we're making a more robust solution that doesn't start on fire. This is my favorite part, how it works. Our intellectual property is based around a robust container mechanism. Up top there on the right, looks like a basic container, but it's a real mechanism. It has features, and it does several things to control fire, thermal runaway events, and other things. We do use commercialized cells. We're experimenting with lithium-ion and nickel cells. The nickel metal hydride cell is already a safe cell developed for hybrid vehicle applications such as the Toyota Prius. However, they're plagued with short operational lifetimes and low power. We're investigating specific unlocks with our container with nickel metal hydride to increase cycles and utilization rates. So with the container, we can improve the nickel metal hydride cells. On the same note, we're applying basic engineering solutions to existing high-powered lithium-ion cells, high-power and high-tech cells. We can prevent catastrophic cell failure and system failure and keep thermal runaway of one cell from propagating to other cells. So we can avoid those big fires like you saw in the previous slide. The market opportunity is immense with the globalist shift to electrify everything from vehicles to home heating. That's created an infinite demand for energy storage and grid batteries. A Department of Energy forecast has estimated that by 2027, there'll be a $15 billion North American market for grid batteries. We propose just to capture a small part of that, about 1.5%. Through extensive customer discovery with grid operators, project developers, renewable project developers, we've honed in on potential first customers, and those would be with data centers and telecom. The data centers are very keen on their power consumption efficiency, and telecommunication companies, cell towers, still have a lot of cell towers powered by diesel generators, and those are, very thirsty. So with those two areas, we plan to hone in and work on that coveted first purchase order for our batteries. As I wrap up, here's a picture of our engineer Quang with a prototype. This is a small scale prototype, something about equivalent to a Tesla Powerwall. But this one is ready to go underground for a long and efficient life. It won't be like mounted on the side of someone's home. This will go underground and operate efficiently. On a final note, we just received a handwritten letter from the Canadian Standard Authority. They're responsible for safety standards of energy systems, among other things. Our contact, Michael, described our solution as a fantastic change to existing offerings in the industry. All right, thank you for everything. If you'd like to, you can scan the QR code. There'll be more information there, and you can ask me questions after the presentation. Thank you very much.
Good evening, everyone. Thank you for being here and for the opportunity. I want to talk to you about travel. Unfortunately for you, I'm going to talk more about how the sausage is made and less about the pasta and wine that usually go with it. So my name is Nick, and my partner Phil is here. Phil, there you go. So we're tackling travel industry's #1 problem, data. I've been in travel, finance, and technology for over 2 decades. Led companies between 10 and 850 people, went in companies from inception to private equity-backed turnarounds for over $500 million. Phil has been in business same time as me in technology and finance, quantitative trading for over a decade, tech for over a decade, including the last 5 years in Amazon with the LXAI team. So together we put this amazing team that's here. And what is it that we're fixing in travel, or sorry, in data? What is the issue? Lack of accurate and updated data. That creates a myriad of different problems. They're usually more perceived in travel e-commerce. So there's over 80% cart dropout rates in most travel websites. The conversion rates is sub 2%. And the most interesting of them all is hotel guest return rate is on average 4%. Think about it, a business where your customers sleep with you, stay with you, create memories with you, and 96% of them never ever come back, right? So, well, yes. It should have come across a different way, but I'm happy I made you laugh. Anyway, so there's opportunities everywhere. And our solution is pretty simple, right? We started by looking where no one else is looking, right? Travel is a $10 trillion industry, largest employer in the world, highly fragmented, highly complex. Nobody looks at travel agencies for, the common belief these days is that travel agencies are dead. There's no more because of Expedia, Booking, and whatnot. As a matter of fact, 12% of all hotel bookings are made through travel agencies. That's over $100 billion of room nights that are sold by travel agencies a year. The issue that they perceive, and they've been growing over 20% over the last 4 years, so they're still growing, amazingly enough. And the issue that they face is over 20% of those commissions that they should be getting from booking those hotels are never getting paid, right? The ones that do get paid take on average 90 days. And the part that is hard to put into numbers is the sheer amount of paper pushing, admin processes that go between both parties to get to that settlement. So our solution is our first product is a fintech-enabled hotel booking platform for travel agencies. It's been designed to completely eliminate all losses, all delays, and all manual work. So think about it. In one side, you have over 20% top-line loss. Top-line loss. Think about a business that loses over 20% of its revenue and thinks it's normal, right? 90% delays, ton of manual work. On the other side, you have money in the bank, straight away, no questions asked. I wanted our slogan to be no-brainer. I was told we shouldn't do that. So we settled for book, pay, get paid. And in addition to the payment part, which obviously is the crux of it, we are aggregating all different booking channels. So the idea is that this becomes a one-stop shop for travel advisors. We are also streamlining workflows from currently seven processes to 2 flows, which are actually 100% automatic as well. And we launched under 3 months ago. Today, we broke the mark of over 1 million hotel rooms in our platform. Our monetization is also pretty simple, 1%. We split 50-50 between buyers and sellers. We're focusing mostly on the luxury market. So most of the travel agency business is highly skewed towards the high end. That's what happens to be my background as well, where we're focusing right now. Our go-to-market, going forward, we're essentially focusing on getting more inventory to create enough critical mass. That inventory, together with purpose-built features that were coming as feedback from our clients, will eventually create that critical mass, which then, together with paired with the exceptional commission performance, right? This will create a flywheel that will bring new participants. Those new participants add more value to the network, and then we continue to grow. We believe that this is a $19 billion a year opportunity. Our competition today are legacy platforms, and they either don't settle commissions at all, or when they do, it's at a very hefty price. In terms of product roadmap, the marketplace that we created right now is essentially the core of the technology and of the business. All of the products that come after that, they essentially are built on top of that same platform. So a single sign-on for travel, you might have noticed that you don't see that in most travel websites, that you don't have a customized customer journey. You don't have a one-click checkout. There is no tailored travel wallet. And the ultimate goal, again, remember from the beginning of my pitch, is data, right? So we want to create the world's largest travel data warehouse. So one day, all of you can travel from point of view of purchase or experience as easy or better than riding an Uber. So that's it. Thank you very much.
I would like to again thank the teams of both Raytheon and Teledyne who contributed so much to this technology. So many former colleagues are here tonight. And thank you for contributing the hardware that supported the networking hour for our event tonight. It's my pleasure to introduce Matthew Greenhouse, who has served on the James Webb Space Telescope since joining NASA in 1997. Dr. Greenhouse has degrees from the University of Arizona and the University of Wyoming. Dr. Greenhouse is the recipient of more than 20 individual performance awards and honors, including the NASA Exceptional Achievement Medal and the Robert H. Goddard Award for Exceptional Achievement in Science. I'm thrilled to introduce Matthew to talk tonight about the amazing James Webb Space Telescope.
Good. Well, thank you everyone for coming out to hear about the James Webb Space Telescope mission. Now, traveling back in time is the stuff of science fiction. But looking back in time is something that we can actually do, and it's a major part of the mission of space telescopes. So how do we look back in time? It works as a result of the finite speed of light. If you look at the person seated next to you right now, you're not seeing them as they are. You're seeing them as they were a few nanoseconds ago. Now, that's because it takes light a few nanoseconds to travel 1 meter from that person to your eye. Now, a nanosecond is a really, really small amount of time. So that transmission delay is completely imperceptible to us. But as we look at objects farther away, it becomes more pronounced. For example, if we had a magic switch that could turn off the sun, and we flip that switch, it would be 500 seconds before we saw anything happen. Why? Because it takes light 500 seconds to travel from the sun to the Earth. So when we look at the sun, we're not seeing it as it is, we're seeing it as it was 500 seconds ago. If we look at the nearest star, we're seeing it as it was 4 years ago. The center of our galaxy, we're seeing it as it was 25,000 years ago, and so forth and so on. And so with space telescopes, we can look back in time to see how the universe formed and evolved. All right, the Webb was conceived, the Webb mission was conceived in the mid-1990s to connect the dots, if you will, between this famous image and this famous image, shown in alongside this cartoon of the evolution of the universe. This image was taken by NASA's COBE satellite. A Nobel Prize was awarded for this image, and it shows us what the universe looked like when it was just a few 100,000 years old, when the universe became transparent and the light from the Big Bang can escape. The colored blobs in this image, the pink and blue blobs, denote temperature inhomogeneities, which are the seeds from which galaxies will eventually evolve. Now, around the same time, the Hubble Space Telescope was launched, and it took the deepest image that it was capable of taking at that time, and it showed us what the universe was like when it was 1 billion years old. And between the epoch seen by COBE and the epoch observed by HST, the Hubble Space Telescope, there is a mysterious, poorly studied epoch known as the cosmic dark zone. And this cosmic dark zone is of tremendous importance because it is the period in the evolution of the universe where the first stars and galaxies formed. Why is it poorly studied? We haven't had the right type of telescope in space to see that epoch, and that was the original impetus for the JWST mission. Now, you've all heard the statement that space is expanding. What do we mean by that? What we mean by that is shown in this cartoon. Here you have a loaf of raisin bread dough that's been set out to rise. Imagine that you're seated on one of the raisins. What would you see? You would see all the other raisins moving away from you. No matter which raisin you sat on, you would see exactly the same thing. And one can see that even though the raisins are not moving through the dough, you still see all the other raisins moving apart. So this is what we mean by space is expanding. We don't mean that the galaxies are flying through space as a result of some kind of explosion, but the space between the galaxies, the space itself, is actually expanding. Well, what does this have to do with the James Webb Space Telescope mission? Well, those first galaxies to form in the cosmic dark zone emit their light in the ultraviolet part of the spectrum. And as that light travels to us through the expanding space, through that expanding raisin bread dough, its wavelength is stretched from the very short wavelength ultraviolet to the longer wavelength infrared. So to see that light today, we have to build an infrared telescope. So that is one of the key differences between the Webb telescope and the Hubble telescope. And that infrared capability that we put in the Webb enables it to do lots and lots of other science. Now, everything we know about the universe comes to us encoded in starlight. And the job of modern astronomy is to extract the information from the starlight. To extract that information, we need all the light. However, all the light does not reach the surface of the Earth. So this is one of the major reasons that we put telescopes in space. Light comes to us in an infinite spectrum of wavelengths, from infinitely long to infinitely short. Much of this light does not reach the surface of the Earth. The visible part of this spectrum, the colors of the rainbow, matches a transmission window in the Earth's atmosphere. So this light reaches the surface, and our eyes have evolved to be sensitive to this narrow spectrum. But our eyes can't see pretty much the rest of it. The Hubble Space Telescope is designed to operate in the ultraviolet part of the spectrum, so shorter wavelength than violet. Our eyes can't see this light, but our skin could be burned by it if you stay at the beach too long. In contrast to Hubble, the Webb telescope is designed to operate from the red end of the visible out into the mid-infrared. Our eyes can't see this infrared light, but our skin can sense it. If you hold your hand near a warm stove burner or a warm radiator and you feel the heat on your hand, what's happening there is your skin is sensing the infrared light emitted by the warm object. And so you can think of infrared light as heat radiation, and the Webb is designed specifically to be exquisitely sensitive to infrared light. Now, the spaces between the stars in our galaxy and others, the so-called interstellar space, it's not a cold, empty vacuum. It's filled with giant clouds of molecular gas, dust grains, atoms, ions, a lot of stuff. Here is one such region of space known as the Eagle Nebula. In this nebula, there are some young hot stars that are pumping out a lot of ultraviolet radiation, which is breaking up the molecules in a giant molecular cloud here and causing that cloud to glow, producing this visible nebulosity, as we call it. Now, the Hubble Space Telescope, early in its mission, imaged a part of this Eagle Nebula to produce this very famous image called Pillars of Creation. So what you see here are filaments of this giant molecular cloud. So this is molecular hydrogen. And you can see the filaments are opaque because there are a lot of dust grains that are mixed in with the gas, and the visible light cannot penetrate that dust. However, if we look at that same object in the infrared with the Webb Space Telescope, the longer wavelength infrared light can see through the dust to reveal processes that are happening inside, star formation in particular. So this is one example of how the Webb telescope will use its infrared capability to peer through visually obscured regions to understand the physics of what's happening inside. Here is another example from the Webb. This is another molecular cloud where lots of new stars are being born. Some have already been born and are outside the cloud. You can see hydrogen streaming off the cloud as UV light impinges on it. You can see a number of embedded new stars here. As this hydrogen streams off the cloud, it moves supersonically, so there are shock fronts that produce a lot of other emission. You can see star formation happening here in the cloud. So the infrared capability allows us to peer into the places of star birth to understand the processes of star formation better than we do. Now, we understand the basics of how stars are formed. Giant molecular clouds in space collapse onto themselves due to self-gravity. And as the cloud collapses onto itself, the pressure inside the cloud goes up. And when the pressure goes up, the temperature goes up. It's much like when you fill your bicycle tire at the gas station, the tire gets a little warm when it's fully compressed. Well, in the cores of these clouds, the temperature gets really, really, really warm to the point where nuclear fusion can occur, and then the star is born. And when the star is formed, it typically has big bipolar outflow jets, as shown in this cartoon, and there is typically a circumstellar disk of material surrounding the star. You can think of that as material left over from the star formation. And as planets, these circumstellar disks are of huge scientific interest because they are the birthplaces of planetary systems like our own. And when planets form inside this disk and they orbit their star, they sweep up material in the disk to cause it to take on this sculpted appearance. And here we have radio telescope imagery of sculpted circumstellar disks obtained with a big radio telescope in Chile. And one can see that by observing these sculpted disks, we can infer the presence of exoplanets without having to see the planets themselves. Here are some examples from the Webb. This is the circumstellar disk around the star Fomalhaut. And here is the Hubble Space Telescope image of Fomalhaut, and here is the Webb telescope's image of Fomalhaut. And you can see that the Webb shows a lot of inner structure in this disk that Hubble can't see. This may be a planet. And just an example of Webb imagery of circumstellar disks that we're obtaining to understand how planetary systems like our own form. Here is another example. If you're sitting near the front, you can see there's a thin black line here. That's a circumstellar disk seen edge on. Here's the big bipolar outflow shown in this cartoon. So we're seeing this stuff in amazing detail for the first time. This is a Webb image that made the cover of Nature just a month ago, again, of one of these big bipolar jets. And here, Webb spectroscopy has revealed the molecular composition of this jet material. Here is another example of star formation near the Earth. This is one of the closest regions where stars are being born near us. This one's about 400 light years away. There are 50 sun-like stars in this cloud. Here's one that has eroded out a cavity in its surroundings in the cloud that gave birth to it. There's a lot of shock-excited molecular hydrogen and hydrocarbons here. So the Webb is showing us these processes in unprecedented detail. Now here you have an artist's rendition of the debris disk around our own star, the Sun, alongside a map of where that debris actually exists. These are chunks of rock and ice left over from the formation of our solar system. So they're very interesting, and understanding them more is a big objective of the Webb telescope mission. Now, recently, we sent a spacecraft out to image for the very first time one of these objects. These are called the Kuiper Belt objects, or trans-Newtonian objects. And the New Horizons mission, which was a Pluto flyby mission, when we finished the Pluto part of the mission, we sent it out to take the very first image of a Kuiper Belt object, and this is what we saw. It turned out to be two objects fused together. And this has since been computer modeled to result from a very low velocity collision, just a few meters per second collision, has shown that objects like this can fuse without either one being destroyed in the process. And this is of great interest for theories of planet formation, in which planets form by successive agglomeration of small particles into larger ones, eventually producing a planet over 10 to the 8 years or so. So we've put special non-sidereal tracking capability into the Webb telescope to allow it to study these Kuiper Belt objects and also the outer planets of our own solar system. Much of the liquid water, most of the liquid water in our solar system may not be on the Earth. Moons of Jupiter and Saturn are believed to contain vast oceans that are covered with a thick crust of ice. When tidal forces act on that ice, the ice cracks, and it can result in a geyser-like phenomena. This cartoon is shown on Enceladus, and here is a Cassini spacecraft image of this phenomena occurring on Enceladus. This is of great interest for the search for life in the universe. We know that from studies of the mid-Atlantic ridge here on the Earth, that there can be rich life thriving on chemical energy, volcanic vents, on the mid-Atlantic ridge, and that life is completely disconnected from the sun. No sunlight reaches the bottom of the Atlantic Ocean. The same thing could be happening in these oceans. And so studying this objective spectroscopically is a major objective of the Webb Space Telescope mission, and we've already started that. This is on Enceladus, a moon of Saturn. The Webb has shown that spectroscopically that this is water, and it's also shown that Enceladus is pumping out so much water into space that it's actually leaving this toroidal ring that completely encloses Saturn of water vapor. And so it's very exciting and interesting, and the Webb will be doing more work on this. This is early Webb imagery of Jupiter and Uranus. Here on Jupiter, you can see Jupiter's great red spot. This is a storm that's been raging on the surface of Jupiter for hundreds of years. Today, we see that the red spot is shrinking, and maybe the Webb will help us understand why it's shrinking, and the Webb may help us understand why the red spot is red. We still don't know why the red spot is red. The Webb has shown us very faint rings of Jupiter and small moons that were too faint for flyby spacecraft to have seen. And the Webb has shown us this remarkable image of the ring system around Uranus. These rings consist of chunks of rock and ice, and the Webb, with its infrared capability, is exquisitely sensitive to rock and ice. And so we're able to see this ring structure like we've never seen it before. Now, when I was a graduate student, there were no planets known outside the solar system. Today, we've identified more than 5,000, and we believe, for all practical purposes, that all stars have planets, with the implication that there are tens of billions of habitable worlds in our galaxy alone. We don't know that they're inhabited, but we have learned how to search for life on them by studying the chemical composition of their atmospheres. So the search for extraterrestrial life is no longer the stuff of science fiction. It is very much a major science objective of NASA. So how do we do it? How can we search for life on an exoplanet that's so faint and tiny that we can barely see it? We do it with a process called spectroscopy, in which we use special optics to spread light out into its component colors so that we can see the emission and absorption of light by individual atoms and molecules in the gas. So here's an example of spectroscopy of Mars, Earth, and Venus. So what is this? A spectrum is a plot of brightness on the y-axis and wavelength on the x-axis. So on this plot of the Earth's atmosphere, you see all these bumps and wiggles. If Earth had no atmosphere, this would be a flat line. But it has bumps and wiggles, so we know the Earth has an atmosphere, and every one of these bumps and wiggles is due to emission and absorption of light by atoms and molecules in the atmosphere of the Earth, and we can identify which atom and molecule is producing every bump and wiggle. And so in this way, we can measure the chemistry of remote objects, and what we're looking for is chemical species that would be indicative of biology. Now, how do we really do it? As we observe these exosolar systems, alien solar systems, as you will, some of them will be observed edge on. So in this cartoon, we have an edge-on solar system, and we have our telescope here with its special optics. And imagine we take a spectrum in this configuration where we have the star and the planet along our line of sight. We take a spectrum. What do we get? We get a spectrum of the star plus the spectrum of the planet's atmosphere. Now we just wait a little while for the planet to move out of the way, repeat the measurement, that's just a spectrum of the star, subtract the two, and voila, we have a spectrum of the exoplanet's atmosphere. Now, I'm making it sound simple. It's really profoundly difficult. The photometry that you have to do to make this work requires precision of parts per million. However, this has been developed into an exact science with the Hubble Space Telescope, and so the Webb will be is doing a lot of this work. The Webb can detect water on an exoplanet that is just a few times the size of the Earth. If we're looking for extraterrestrial life, why do we care about water? It's not because alien life might get thirsty and need something to drink, but rather for the organic chemistry of life to occur on a planetary scale, one needs to have a liquid solvent available on a planetary scale, and water is what we're most familiar with. So here are some examples of Webb transit spectroscopy of exoplanets. The first thing that you can see here is that we have squiggly lines. So these planets have atmospheres. And as I promised, we can actually identify what atoms and molecules are producing all these bumps and wiggles. Here we've discovered potassium, water, carbon monoxide, even sulfur dioxide in this exoplanet. Sulfur dioxide is very interesting because that is formed by chemistry in the atmosphere as opposed to on the surface. So this work is ongoing with Webb, and we are cataloging and analyzing the spectrum of lots and lots of exoplanets with Webb. Here's another recent example where we've discovered methane and carbon dioxide, and we got a hint of a very intriguing molecule called dimethyl sulfide. Dimethyl sulfide, at least on the Earth, is only produced by biological processes. So if we can discover that elsewhere, it'd be very interesting. This detection does not yet meet the rigid statistical standards that scientists put on themselves to claim a discovery. So this is going to require a little bit more observing time with the Webb, but it's an example of how interesting and fascinating this kind of work can be. All right, when we first put pencil to paper or marker to whiteboard on what kind of observatory we had to build to do that kind of science, we realized that we needed 7 times the light gathering capacity of the Hubble Space Telescope. And we also realized that we needed Hubble's ability to see fine detail, angular resolution as they call it, but we needed that in the infrared part of the spectrum. Turns out that also requires a big mirror. And as I mentioned, we needed to have observing capability spanning the optical to the mid-infrared. So when we realized those 3 things, we then realized that we had 2 enormous problems that almost stopped the project completely dead in its tracks. Well, you know that we solved those problems, but let's talk about it. The first is that to get 7 times the light gathering capacity of Hubble, we need a primary mirror that's bigger in diameter than the biggest rocket. That's problem number 1. Problem number 2 is to build an infrared telescope, one has to make the telescope very, very cold. How cold? Almost minus 400 Fahrenheit. Why? Well, everything above absolute zero emits light. So if you had infrared goggles on right now, you would see the walls and floor of the room glowing in the infrared. Your body would be glowing in the infrared. If we didn't make the Webb telescope very cold, it would be blinded by its own infrared emission. And the problem that this presented was that then and now, there is no mechanical refrigerator powerful enough to cool something as big as the Webb to such a low temperature. So those were our 2 problems. Let's take a look at how we solved them. Let's talk about the thermal problem first. We didn't put the Webb in orbit about the Earth. the way Hubble is and the way most satellites are. We put it in a special spot in space called the second Lagrange point of the Sun-Earth system. That's a mouthful. We just call it the L2 point for short. And the L2 point is 1 million miles away in the anti-sun direction from the Earth. All right, how does that help us cool the Webb telescope? Well, as the Earth orbits the Sun, this pattern of Lagrange points, of course, orbits with it. And so one can see that if you place an object at the L2 point, all the sources of heat on that object, the Sun, the Earth, and the Moon, will always lie in the same direction. And so then we realized, well, if we deploy a giant sun shield to block the light from the Sun, the Earth, and the Moon, then the telescope can cool passively by simply radiating its energy away to the cold darkness of space. And so that was the solution that we adopted. However, for the Webb telescope to be useful, we have to be able to point it to any object in the sky. And it always has to be in the shadow of its sun shield. So we sized the sun shield so that in this diagram, we could point the Webb 5 degrees toward the Sun and 45 degrees away from the Sun, and we're still in the shadow. So we have an arc on the sky that's 50 degrees long. And now, just looking at this diagram, you can see that if we rotate the Webb about the Earth-Sun line, about this line, that doesn't spoil our shadow situation at all. And so now this arc becomes an annulus that covers 35% of the sky. So at any instant in time, the Webb can observe 35% of the sky and still be in the shadow of its sun shield. Now, as the Earth orbits the Sun, we're rotating about this axis, and you can see that this annulus will sweep over the whole sky every 6 months. So every 6 months, the Webb can point at any spot in the sky and still be in the shadow of its sun shield. And that's basically how we cooled the Webb. Now, we didn't put the Webb exactly at the L2 point. We put it in a small orbit about the L2 point. Why did we do that? Well, we're generating electricity on Webb with solar rays. It takes about 2 kilowatts of power to run the Webb. And so it was important that we keep the Webb out of the Earth's shadow. And so for that reason, we put it in this small libration point orbit about the L2 point. That orbit is unstable, and so it needs to be maintained with station-keeping thrusters. And the propellant that we have on board is modeled to last about 20 years to maintain that orbit. And so that's how we solved the cooling problem. And finally, another good reason why we put the Webb at the L2 point is that if an object is at the L2 point, the telecommunications range to the Earth remains constant as long as the mission lasts. And that's very important for our ability to get the data back from the Webb. We're transmitting it back with radio transmission. All right, let's talk about that sun shield. The JWST sun shield has an SPF of 1 million. So if you had this thing on the beach, you would be very well protected. It is literally the size of a tennis court, 70 by 40 feet. It has 5 layers to get that SPF. Each layer is made of a heat-resistant plastic-like material called Kapton. Each layer is thinner than a human hair. Each layer has to have a special curved shape. And those of you who sew know that to make something curved out of flat cloth, you have to have seams. And so each layer is actually a quilt of 50 pieces with 7,000 inches of seaming. Here it's not done with needle and thread, but thermal spot welds. The sun-facing layer is coated with silicon, so it really does look pink in reality. The remaining layers are coated with aluminum. Developing this sun shield and figuring out how to deploy it reliably was really one of the most challenging aspects of the Webb mission and one of the things that we're most worried about. Here is an example of some testing done on the sun shield. The sun shield is folded up in a containment pallet here, and these telescoping booms are pulling it out of the pallet. These mylar tables are there for gravity offloading. They're not there in space. but you can see a person appearing in the middle here. That gives you a sense of scale. And this is basically exactly how it's deployed in space. These spreader bar assemblies around the periphery will spread apart the 5 layers, and then they also tension a cord that runs around the periphery of each layer. All right, you get the idea. All right, so some facts about this sun shield. Getting that thing deployed involved 140 release mechanisms, 70 hinge assemblies, 8 motors, all of which are single points of failure. Any one of those things didn't work, the whole mission is over. So remarkably, we got permission to launch this thing with all those single points of failure. 400 pulleys, as many meters of cabling. This was really difficult and scary stuff. But this was the highest risk part of the mission, but it all worked perfectly, and Webb is operating at its intended temperature. Okay, so what did we do about the primary mirror being bigger in diameter than the biggest rocket? Well, instead of building one 6.5 meter diameter mirror, we built 18 hexagonal segments that are mechanized to play together as if they were each segments of the same mirror. And that allowed us to fold the telescope up inside the fairing or nose cone of the rocket that we used. We used a French rocket called the Ariane 5. It has a 5-meter diameter fairing, and the Webb was designed to fold up inside that fairing. This is an end view, so you can see there's not much space left over. And this is launched from Kourou Launch Center in French Guiana, which is on the east coast of South America. The payload is 6.5 metric tons, and lots and lots of deployments needed. All right, the Webb telescope mirror segments are not made of glass, the way most telescope mirrors are. They're made of a metal called beryllium. Why did we use beryllium? Well, when the Webb is in the shadow of its sun shield, pointing at different directions around the sky, there are small temperature gradients that will form in the mirror. And we didn't want those temperature gradients to spoil the shape of the mirror. So we had to find a material that had a low coefficient of thermal expansion at this enormously cold operating temperature of minus 400 Fahrenheit or 50 degrees Kelvin. And it turns out that beryllium has that property. The beryllium starts out in a powder form. We compress it under tremendous heat and pressure to make what's called a billet of material. And then after we go through all the trouble to do that, we machine away almost all the beryllium. So this is the back side of a flight mirror segment, and this is the front side. You see laboratory equipment reflected in the mirror there. And you can see that we're lightweighting this mirror as much as we possibly can. Whenever one designs something to fly, whether it's an aircraft or spacecraft, weight is a major engineering driver. The Webb telescope mirror segments are about 6 times lighter than the Hubble mirror in aerial density, and they represent the current state of art for lightweight telescope optics. Now we have another problem. How do we polish telescope mirrors? We rub on them with gritty stuff until they get smooth and shiny enough. That's inherently a room temperature operation. So if we're going to polish the mirrors at room temperature and then use them at minus 400 Fahrenheit, it means that we have to put in the wrong shape at room temperature to get the right shape at the operating temperature. This is done through the magic of computer modeling, but computer modeling is not perfect. So we had to follow an iterative process in which we would polish the mirrors part way, and then we would put them in a specially instrumented space simulation chamber at Marshall Space Flight Center in Huntsville, Alabama, where we could cool the mirrors down to their operating temperature, observe them with special optics test equipment to see how our model and reality are tracking to each other. Then we would make iterations in the process to produce this result. And this is real data on a real flight mirror segment. So what do we have here? This is an interferogram of the surface of the mirror. And the colors denote relief, peaks and valleys. And so this is the mirror at room temperature. We take that mirror and cool it down to the operating temperature, and all those peaks and valleys go away, and you're left with a nearly perfect mirror figure. And so that's the process that we followed. It took a long time to get all the mirror segments to this result, and that's one of the reasons why it took so long to build the Webb telescope. Now, when we got all the optics made and put together, and we got all the science instruments built and integrated with the telescope, we then put it into a special mobile clean room, if you will, that preserves the Webb in the ultra clean special environment that it needs to stay in to remain qualified to fly in space. But this container turned out to be too big to put in any kind of transport aircraft. And so instead, we put it on a special roll-on, roll-off transport ship. And we shipped out of Seal Beach, California, just south of LA, went through the Panama Canal over to Kourou Launch Center in French Guiana. It took us a couple weeks to make that trip. This is the first time NASA's delivered a payload by boat. We had great weather, and this all worked out well for us. All right, now we're at Kourou Launch Center, and we're in an elevator that's riding up alongside the Ariane 5 rocket in the vertical assembly building. There are work platforms set up at various points along the rocket where people are getting the rocket ready to fly. We're going to the top, where the Webb telescope is being integrated to the rocket's payload adapter fitting. And this is the very last view of the Webb telescope on Earth. This is done in a very clean environment. The spacecraft is fueled here, which is why they're wearing that safety gear. And then the nose cone or fairing is integrated axially in the case of this rocket. And then the rocket is rolled out on a crawler vehicle. It actually goes very slowly. You can walk alongside it. It's, of course, sped up here. And we moved it out to the launch pad, and then we launched it. Idea here. All right, the launch was very successful. The first deployments that happen are the solar arrays come out so we can be power positive. We're operating on batteries. You saw the high gain antenna come out so that we can begin talking. This last picture you saw is a real picture. We actually had a camera on the upper stage to watch the JWST come off the rocket. We followed something called a direct transfer trajectory to get out to the L2 point. We didn't orbit the Earth even once. This is how the telescope unfolds. You see the secondary mirror come down on a tripod like that. These are some thermal radiators. And here you see the wings of the primary mirror unfold much like a round drop leaf kitchen table. All right, now we have 18 hexagonal segments that make up that mirror. So when we got out and we first pointed the telescope at a star, we have 18 telescopes. And we're going to get 18 images of that star. Now the mirror segments are mechanized in 7 degrees of freedom, the 6 you're familiar with, plus radius of curvature. And so we can move each mirror segment one at a time to figure out which image goes with which segment, and then we superposed all 18 of those images on top of each other, and then we used special interferometric optics in one of our science instruments to adjust each mirror segment to be coplanar with its neighbors to a small fraction of the wavelength of light being observed, and that produced produces a nearly perfect image. And the Webb is exceeding its image quality requirements by about a factor of 2. All right, so Webb is giving humanity its first high-definition view of the infrared universe. What do we mean by that? This shows what we mean by that. These are our prior infrared missions, WISE, which operated from 2009 to 2011, Spitzer, which operated from 2003 to 2020, and now JWST. These images are the same spot on the sky. These 4 stars are these 4 stars are these 4 stars. But you can see how much clearer the Webb image is over the predecessors. What's going on here is our ability to see fine detail is determined by the wavelength divided by the size of the telescope. The WISE was a tiny telescope, only 40 centimeters in diameter. Spitzer was only 85 centimeters. The Webb is 6.5 meters. And so it's the size of the mirror that's doing the magic here. All right, so with Webb, we wanted to see galaxies in that cosmic dark zone when the universe is only a few 100,000 years old, and we are actually able to do that. These are spectra of galaxies. And we're using a feature in the galaxy spectrum, an absorption feature of atomic hydrogen that allows us to measure the redshift of the galaxy. And we're seeing galaxies out at redshift 13 when the universe is very, very young. And this is somewhat of a surprise that we are seeing these mature galaxies at such an early point in the universe. We're able to do spectroscopy on those galaxies to see their chemical composition. And we're able to see with our imaging capability the morphologies or shapes of the primeval galaxies, and that is also somewhat of a surprise. We didn't expect to see galaxies that had such symmetric regular morphologies in the very early universe, the way we see them in our local universe. With the Webb, we're also able to measure gas motions within galaxies and also pick apart the emitting regions of various chemical components within galaxies. So we can tell, for example, where the molecular hydrogen in the galaxy is being emitted and compare that to atomic hydrogen or iron, and develop a complete physical picture of galaxies for the first time with this infrared capability. I remember we said in the beginning that the universe started out opaque and then became transparent. And that process results from the first stars and galaxies form and ionize out their surroundings. So they form these bubbles of ionized plasma, and the bubbles grow and coalesce till pretty much all of space is ionized, and then the light can escape. And with Webb, we're actually able to see this process happening. So it's very, very exciting as we look back into the early universe. This slide, sort of bookends my career. This is an image from the very first scientific paper I ever wrote when I was a graduate student, and it was before we had detector arrays. In these days, the detectors just had 1 pixel. And if you wanted an image, you had to raster that pixel over the sky. Okay, so this is an object called the Ring Nebula, and it is what happens to a star like our sun when it runs out of fuel. The sun will throw off its atmosphere to produce this nebula. And so that's 1988 versus 2023 is quite a bit more detail there. This is what happens to a star that's much more massive than the sun. When it dies and throws off its atmosphere, it results in a giant explosion called a supernova. These are some of the biggest explosions that occur in the universe. This is a Webb image of the Cassiopeia A supernova. This supernova actually occurred during recorded history, just 340 years ago. So people actually wrote about this in literature. They would have seen a new naked eye star star appear in the sky. And this it is in explosions like this that all the heavy elements of the periodic table are formed. So the calcium in our bones, the iron in our blood, the gold and silver in our jewelry were all made in supernova explosions like this. We've seen really unexpected, unusual phenomena with Webb, such as shown here. This is episodic dust ejection from a late-type star, and this cartoon is showing the interpretation of this remarkable bullseye pattern of dust emission that we're seeing here. All right, so how does the universe work? How did we get here? Where are we going? And are we alone? The Webb mission, these are the central questions that drive NASA astrophysics. And the Webb mission enables the next step in humanity's quest for the answers to those questions. And you can join that quest. The people that do this kind of work come from all walks of life, all backgrounds, every kind of engineering that you can think of, and lots of science disciplines are involved in building missions like this. There's a quote that I like to read. The book of nature lies continuously open before our eyes, but it cannot be understood without first learning to understand the language and characters in which it is written. It is written in mathematical language, and its characters are geometrical figures. That's as true today as it was 400 years ago when Galileo said it. So to work in this kind of business, of course, one needs to go to college. If you're already in college, I saw some that we have young people here. Stay in college. Study whatever you love. But if that happens to include science, engineering, and math, one can consider space science and aerospace as a very realistic career objective. If you want to know what it's like, NASA has excellent intern programs for every level, from high school to senior faculty, and there's one-stop shopping here to apply for those programs. And let's say you want to get involved in this kind of research, but you don't want to go through all the trouble to get a PhD and become a scientist. You can do that too. NASA has a program called Citizen Science, where with whatever your background is, you can apply to become part of a NASA research team and really work with that team in the data. Some of the image processing that you saw was actually done by citizen scientists. And despite the name of the program, you don't need to be a US citizen to join that program. Okay, what's next? This past July, we launched the Euclid mission. That's a European Space Agency mission on which NASA is a partner. And that mission has been very successful, and it just released its first science imagery, I think day before yesterday. The infrared detectors on that were made by Teledyne of local interest. Then in 2024, we will commission the Vera Rubin Observatory. This is a giant ground-based telescope in Chile that will usher in a new type of astronomy called time domain astronomy, where the emphasis is on what changes in the night sky as a function of time. Then in 2027, NASA will launch the Roman Space Telescope. Its mission is to study dark energy and also to develop some technology that we need to observe Earth-like exoplanets on the Habitable Worlds Observatory, which is the next big mission that will follow the Roman Space Telescope after it's launched in 2027. So this Habitable Worlds Observer, as we call it, will be a UV optical version of the JWST. It'll be the same size, but designed to work in the UV and optical. Okay, and those are my remarks for tonight, and I'll take questions for as long as they let me.
We have some questions from the audience. Has the JWST changed our understanding of the age of the universe?
Okay, great question. It hasn't changed our understanding of the age of the universe. However, it is revolutionizing our understanding of how galaxies form and evolve. The Webb is showing us the early universe for the very first time in some sense, and we're seeing that galaxy evolution happens much, much faster than we thought. And so stay tuned for that. The universe age isn't changing, but our processes of galaxy formation are changing. Yep.
You talked about the solar shield. Who built the solar shield, and how long did that take in development?
Northrop Grumman was the prime contractor on the Webb telescope, and they did do the sun shield. These giant deployments are somewhat of a specialty of theirs, and it took a long, long time, from basically '97 until launch.
How did NASA come to work with the IR companies that are located here in the Southern California region?
Yeah, okay. Well, we issue solicitation, business solicitations, and people, answer those solicitations. And so we're very fortunate that we have companies like Teledyne and Raytheon to make the eyes of JWST, and they all happen to be here in this area. But without that technology, which doesn't exist anywhere else in the world, none of this would be possible.
Can you briefly describe the process by which NASA chooses the studies that JWST performs?
Okay. It's very interesting. NASA doesn't set its own objectives. Okay. Every 10 years, the National Science Foundation is tasked by law to do what they call a decadal survey. And they solicit input from the U.S. science community. Thousands of white papers are written and sent into this decadal survey process. And every 10 years, the National Science Foundation sets the science priority for NASA. And NASA follows those priorities to the letter. We don't question them, we just salute and follow those priorities, and that's how it's done.
Can JWST detect oxygen in exoplanet atmospheres?
I think so. Yep.
And how is color added to the images that you've displayed today? Okay.
So we said that our eyes can't see the infrared. So how is it that we're looking at photographs like that? The infrared instruments have filters, just like your regular camera. There are narrow slices of wavelength that are observed in images like this. And then one can one can replace the infrared colors that you measure with those filters with corresponding optical colors to simply create an image that you can see optically, and is done in a scientifically accurate way.
You mentioned that JWST sits at the L2 point. Will any of the other NASA telescopes be at the similar point as L2? Yeah,
this is turning out to be a really useful place for lots and lots of space science. And so the Roman Space Telescope I mentioned will go there. Euclid is there now. There's there's like a half a dozen missions that have gone to the L2 point.
You've spent your entire career working JWST, and it's such an amazing legacy. Of all the scientific discoveries that have been made over the last year and a half, what excites you the most today? Well, boy, and why?
Like a lot of astronomers, I'm pretty interested in the exoplanet results. The whole field of exoplanets has exploded around us in just the past few years. It's the fastest growing area of astronomy, and it's pretty exciting to be measuring, the atmospheric composition of all these other worlds. And there's no question that we will eventually find life, not necessarily with JWST, but we really have the tools in hand now to study these other worlds, and it's just super exciting. Yeah.
Please join me in again thanking Dr. Matthew Greenhouse for the amazing talk.
Thank you.